So, now let us see the radial steady state heat conduction through a spherical surface. Already we have derived the result for one dimensional heat flow, but that can be extended to radial flow for cylindrical and spherical surfaces. First of all, see spherical surface. So, we need to understand here the same laws can be applied, one dimensional laws for one dimension can be extended to radial flow. So, we have two concentric spheres of radii r1 and r2. So, the inner surface is maintained at temperature theta 1 and the outer one is maintained at temperature theta 2, and the material medium which is inside this, the annular region is filled with the material medium, that this is the medium whose conductivity is K. We wish to study how heat current flows in steady state, how the heat current flows, what is the temperature at different radial distance, and given Q1 and Q2 the temperature of the inner and outer shell. So, consider a spherical shell whose inner wall is of radius r1 and is maintained at temperature theta 1 and whose outer radius is r2 and is at constant temperature theta 2. The conductivity of the medium, the thermal conductivity of the medium is K. So, now what we do? So, we just imagine an annular region, this is the annular region, a differential ring whose radius is r and this annular width is dr. Now, the inner part has a temperature theta and here theta plus d theta. So, now let us shade this. So, this is the annular width I am considering. So, consider the heat flow through a differential means small, differential annular region of radius r and radial width dr. The temperature across its ends, that is radial ends, are theta and theta plus d theta. That means inside of this its radial this theta and outside it is theta plus d theta. So, let us applying Fourier's law of heat conduction, steady state heat conduction. Every time I not required to write steady state heat conduction, simply heat conduction will work. The heat conduction dq by dt is equal to minus k d theta by dr. So, what I wanted to tell is that in place of dx I will write dr, because this is radially varying. So, I can apply one dimensional formula along the radial direction. So, this will give us I is the heat current at steady state. I is the heat current flowing through all cross sections is equal to minus k d theta by dr, and here area of cross section will also come. So, now let us use this formula to derive the expression for the current conduction. Now, so you see heat current I can be written as minus k, area is 4 pi r square. You see here, this is the element of, this is our element. So, you see heat current flows along this. So, how much length the heat current has to cross is dr, and how much area it has to cross, the surface area A. So, this area of cross section is 4 pi r square, and the temperature difference is d theta, and the distance, that is the distance between the regions of temperature difference, is here dr. So, we will put this I dr by r square as minus 4 pi k d theta. Now, if I integrate both sides, r varies from r1 to r2, theta varies from theta 1 to theta 2. This is I dr by r square gives on integration minus 1 by r, and this integration is from r1 to r2, that is minus 4 pi k, this is theta 2 minus theta 1. This is again you can take out minus. So, I have taken out this minus. So, it will be 1 by r2 minus 1 by r1, that is 4 pi k theta 2 minus theta 1. So, this is again r1 r2, and this is r1 minus r2, 4 pi k theta 2 minus theta 1. So, now I will write. So, you see here, let it again, I can take minus here. So, this r2 r1 will come. So, I will write this 4 pi k theta 1 minus theta 2 by r2 minus r1 by r1 r2. So, on simplification, this comes out to be theta 1 minus theta 2 upon, this is r2 minus r1 by 4 pi k r1 r2. So, let us write this as thermal resistor. So, you see here thermal resistance, the thermal resistance of a spherical conductor is given by RTH, that is for a spherical conductor, will be given by R2 minus R1 by 4 pi k R1 R2. So, this is the formula that we can be directly using for the thermal resistance of a spherical conductor. Now, let us see that what will be the temperature distribution throughout this spherical conductor, for which again we will be using this formula. Now, let us study the temperature distribution on this system. So, temperature distribution in the spherical region. So, we have taken the case that the inside radius r1 has a temperature theta 1 and the outer radius has a temperature theta 2. So, as a function of r, I want to know what is the temperature theta as a function of r. This is what I want. So, what I do? So, I consider this portion only. So, now you see heat current I is the same at steady state at all the cross sections. So, now I will use the formula that I is equal to the steady state heat current will be Q heat flows from Q1 from theta 1 to theta 2 by RTH. So, the thermal resistance of the whole spherical region. So, thermal resistance RTH formula was R2 minus R1 by 4 pi K R1 R2. This was the expression we derived from our previous discussion, that the thermal resistance of the spherical conductor is this much. So, I will be equal to this. So, we got I as 4 pi K R1 R2 by R2 minus R1 theta 1 minus theta 2. This is equation number 1. Now, I am interested in calculating theta here. So, again I the only if I consider this portion of this. So, I will be theta minus theta 1. So, that is theta 1 minus theta 1, this is theta 1 minus theta will be equal to thermal resistance of this portion, that is equal to how much, theta 1 minus theta upon this portion of thermal resistance means R2 means only R minus R1 by 4 pi K R R1. So, the same I will be using. So, 4 pi K R1 R2 upon R2 minus R1 theta 1 minus theta 2 is equal to here 4 pi K R R1 theta 1 minus theta by R minus R1. So, 4 pi K 4 pi R1 R1. So, now we got R2 theta 1 minus theta 2 upon R2 minus R1 is equal to R theta 1 minus theta by R minus R1. So, we wish to calculate theta. So, this implies, so we will write theta 1 minus theta as by R into again R2 by R2 minus R1, then theta 1 minus theta 2. This is the expression we get. I have to calculate theta. So, theta we will bring this side will be theta 1 minus this quantity. Let us arrange it properly, R minus R1 by R2 minus R1, that is theta 1 minus theta 2. This is how the temperature varies with R. Temperature varies with R like this. So, this is how the current conduction in spherical conductor takes place. So, now let us see one more example. So, here I have again the same spherical conductor with R1 as the inner radius whose temperature is theta 1, R2 is the outer radius whose temperature is theta 2. So, this is the conducting medium of conductivity A. Now, find the radial distance R at which the temperature is the sum of the temperature of the average of the temperature of theta 1 and theta 2. Theta is theta 1 plus theta 2 by 2. So, let us find the region where temperature is theta 1 plus theta 2 by 2, that is the average temperature of these two. So, what we do? So, we want the temperature of this place. So, the heat current, the total heat current and the heat current through this portion is the same, that will be equated. So, heat current I is given as theta 1 minus theta 2 by that thermal resistance of the whole spherical, that is the R2 minus R1 upon 4 pi k R1 R2. Now, again we use this, that the thermal resistance of this. So, heat current through this one will be only theta minus theta 1, this is theta 1 minus theta by this is R minus R1 by 4 pi k R R1. So, the same expression we are again using, this 4 pi k will cancel out. So, we will have theta 1 minus theta 2 into R1 R2, that is R2 minus R1 is equal to R R1 by R minus R1 into theta 1 minus. So, here theta is theta 1 plus theta 2 by 2, we will substitute is this R1 gets cancelled, we are interested in R. Let us simplify theta 1 minus theta 2, we have R2 by R2 minus R1, here only R by R minus R1, this is 2 theta 1 minus theta 1, that is theta 1 minus then theta 2 by 2. This one cancels. I am interested in R, I will bring this R here, R minus R1 by R is going to be R2 minus R1, this R2 will go this side, so it will be 2R 2 and 1 minus R1 by R, then becomes R2 minus R1 by 2 R2. Then again you see here we will put 1 minus R2 minus R1 by 2 R2 as R1 by R, 2 R2 minus R2 only R2 plus R1 by 2 R2, that is R1 by R, implies R will be equal to 2 R1 R2 by R1 plus R2. So, at this radial distance the temperature you see is equal to the average of the temperatures of these. So, thus you see here how I have used the idea of the thermal resistance for a spherical resistor and the idea that the heat current is the same at steady state. So, this is the way which is used to calculate the temperature distribution or the temperature at a desired points. Now, let us see once again that if we have two spherical thermal resistors in series, then how to calculate the net heat flow. So, now we are interested in spherical thermal resistors in series. So, we have two thermal resistors that are spherical. So, this is R1, this is R2. So, you see up to this region we have one spherical, that is K1, this is one resistor and we have another resistor with K2 thermal resistance and that extends from R2 to R3. This is theta 1 and this is theta 3 suppose. So, let us call it theta 3. Okay. So, we are interested in knowing what is the heat current through this composite spherical thermal resistor. So, you see here my expression general will be I is equal to the theta 1 minus theta 3 by R equivalent, where R equivalent is the equivalent thermal resistance. Now, I will write R equivalent, these two thermal resistors are in series. So, For series I have formula R1 plus R2. This will be further written as R1. So, this thermal, let us write this thermal resistors may not be confused with small r, that is the, let it be, suppose I say it is A, this is B and this is C, so that it should not be confused with the R's. So, here what we do, the R equivalent is equal to R1 plus R2, where R1 and R2 are the thermal resistances of these spherical conductors. So, this RQ is equal to R1 becomes B minus A, that is R2 minus R1, the radius difference, by 4 pi K1 AB, plus for this it will be C minus B by 4 pi K2 BC. Thus, we have I is equal to theta 1 minus theta 2, the temperature difference, by B minus A 4 pi K1 AB plus C minus B 4 pi K2 BC. This is how the current, how much will be the net steady state heat current through this composite spherical resistor, thermal resistor or conductor, whatever we say.